Hello, peoples. This video is intended to give a basic overview of circular motion as it relates to orbit caused by the force of gravity. We discussed this in class, and when I asked you to visualize what orbit is, most of you explained you saw planets or satellites or something going around a central object moving in a circle. I asked you what the what forces cause this, or to draw a free body diagram, and you said gravity. And that's really it. Orbit is really, like, a simple definition is circular motion. And circular is in quotation marks. I mean, it's not exactly circular, but for our purposes, it's okay. Yes, it's elliptical, slightly elliptical, sometimes exaggerated, but for the most part, it's pretty darn close to circular. So circular motion caused by gravity. Oh, gravity acting towards center. We'll leave it at that. And by towards center, I'm talking about the center of a circle. So let's draw that out. If this is a planet, we'll call it Earth. We'll call it San Diego. I wish I could quote Anchorman better there, but I won't. Anyway, we put a satellite here. That satellite is moving in a somewhat circular path around our planet here. And if we were to draw a free body diagram, as we always do with problems involving forces, guess what? It would be one force, the force of gravity. I'm writing it for capital G for mostly Physics 1, because that helps separate it from the old way we wrote it, which was FG, but it doesn't matter how you write it. Either way, the math that goes after is what's important. Speaking of the math that goes after, well, that's your free body diagram. It doesn't get much easier than one force in your free body diagram. Your next step is to write out the sum of the forces that cause this satellite to move in a circle, hence v squared over r. You've got one force, and in this case, it's the force of gravity. That's it. Like no normal, no nothing, no forces at angles, literally one force on the left side of the equation. Wow, this is tough. Then the expression for gravity that we have derived in class is G. In this case, we'll go with the mass of the Earth, the mass of the satellite over the distance between their centers squared, that's what the R represents, causes mv squared over r. Which m is that? Is it the Earth or the satellite? Well, a few things. V squared over r is accelerate. Which mass is accelerating? That's one way to do it. Which mass has a velocity that is moving in a circle of radius r? I don't know. Can you figure it out? Am I being sarcastic enough? Yes, it's the satellite. V squared over r. And the mass of the satellite divides out. Surprise, surprise. Gravity doesn't care about the mass of the object. One of the distance between centers divides out, and you are left with not much. You're left with, I'm going to rewrite it this way, v squared, I don't know why that did that, is equal to g, mass of the thing in the center of the circle, over r, which I don't want you to memorize. However, if you are AP and watching this video, or even Physics 1, knowing that the orbital velocity is equal to gm over r, or excuse me, the square root of gm over r, that's great. That's wonderful, quick, multiple choice. You don't have to spend time deriving it. However, if this was a test question, I would expect you to probably, at the minimum, write your opening statement, especially AP on the AP exam. You better write this or you lose a point. Your opening statement means I'm going to do second law for an object moving in a circle. Your next step can go to here, and then your final step will take you here. That's what I'm expecting from all of you on any problem, on any assessment in AP on a free response question. That's what they expect. However, the shortcut is great if you know it for multiple choice. Let's take this a little further, because that's it. We did some calculations in class, but we have this friend. You know who I'm talking about. I'm talking about V is 2 pi r over the period. And we can bring this friend to the party. And if I do, I get, 2 pi r over t squared. Careful, square every term. 4 pi squared, r squared, over t squared. As I wrote r, what am I doing there? I don't know. Over t squared equals gm over r. I'm just going to cross multiply a little bit of this, a little bit of that. I get 4 pi squared r cubed equals gm t squared. Now, this is not an equation at all. This is not an equation. However, I did substitute the 2 pi r over t in for the v squared and just, worked out a little algebra. This is nothing to memorize. You should be aware of the r cubed to t squared relationship. That does come up often in our class, but other than that, don't try to memorize this. This is just algebra. I just substituted something in and I can keep going from here, but we're not going to. I do want to bring up one last thing, and then this video is done. Sometimes you'll see a problem where there's a planet and a satellite somewhere over here, and it's orbiting. I just can't draw a big enough circle. You might be told that the satellite is some altitude or distance above the surface of the planet. That's great. That is not the r that's in the expression that we derived up in here. R is distance between centers, and at the same time, the problem may state like, the radius of the planet. Neither of these is the r we care about. The r we care about for the math that we derived when you do v squared over r, we're talking about distance between the centers of the objects. So in that case, the r that we care about, the orbital distance, that's center to center, is actually equal to the radius of the planet plus the altitude. I mean, the picture helps, I hope. Our planet and plus the altitude. I'm trying to keep the colors here, but there's a little bit of a lag going on here. Plus the altitude, or height above surface. This, again, is not an equation. It's just a visual representation of what's going on. You could be given the altitude and the radius of the planet, and you have to find r, or maybe you're given the orbital radius, or you solve for it in your math, and you know the radius of the planet, and then it could say how high above the surface is this satellite. Something like that. But anyway, let's recap this puppy and call it a day. So a little bit of a summary here. In class, we derived an expression for the force of gravity, which can be written as g, which is a constant, mass 1, mass 2 over r squared, or gmm, where there's lowercase, capital, whatever you want to do. M. I mean, it's up to you. However you like to write it, it's fine with me. And this is the force of gravity, hence Fg, between two masses, hence m1, m2, or m, little m, big M, separated by distance r between their centers. Okay, it's center to center. Orbit, as we discussed in class again, is just circular motion, or nearly circular, hence the quotes, caused by the force of gravity acting towards the center of the circular path and the object's inertia. But let's not get too technical. We can discuss that in class. The moving mass will always divide out, or it's always a smaller mass, but whichever mass is moving does divide out. That is worth knowing and then proving algebraically while setting up the problem. And since we do sum of the forces equals mv squared over r, don't forget, we can bring v equals 2 pi r over t to the party and keep going. We can get the orbital period involved here. So anytime you see period or frequency, we're going to be bringing in 2 pi r over t. Don't memorize v equals the square root of gm over r. However, it's okay to memorize it. I know it sounds stupid, but I should probably say, don't just start an orbit problem with that equation. Like, oh, it's orbit, use this equation. No, just no, you will not receive credit. Do what you've been doing for a long time. Draw a free body diagram. Do the sum of the forces. Set up your expressions. And then lead algebraically down to what you'll always get, which is v squared equals gm over r. However, you should also know it for the multiple choice. It is very good and quick if you need it, especially AP. And last thing, just watch for words like altitude or height above the surface, because that is not R when it comes to the orbital radius. You got to learn to deal with that. We drew a picture and just discussed that about 1.5 minutes ago. Anyway, 1.5? No way. This video is worth 3 out of 5 stars, and I wouldn't change a thing.